Some number patterns look like party tricks. These two look like party tricks, but turn out to always be true. Here's the first one involving Armstrong numbers. 1 cubed plus 5 cubed plus 3 cubed is 153, which is just the digits 1, 5, and 3 concatenated. It keeps going. 16, 50, and 33, all cubed and added, gives 165033. Finally, this works with 3 digits as well. Every time, the sum of the cubes is the 3 bases written one after another. To begin to prove this, we have to think what these numbers really represent. We begin by writing d for 10 to the power of n. These are simply a sixth of d, a half of d, and a third of d, each rounded down. Look at what these are in digits. A is a 1 followed by n minus 1 sixes. B is a 5 followed by n minus 1 zeros, and C is n threes. This means all 3 of these numbers are exactly n digits long. For n equals 3, that gives the numbers 166, 500, and 333, exactly the third row. We can compute these floors by using the fact that for every n at least 1, 10 to the power of n leaves a remainder of 4 mod 6, remainder 0 mod 2, and a remainder 1 mod 3. So subtract these remainders and divide. A is d minus 4 over 6. B is d over 2, and C is d minus 1 over 3. Next, what does the concatenation mean algebraically? Because each block is exactly n digits wide, putting them all together is just shifting by powers of d. So the concatenated number is a times d squared plus b times d plus c. Now we have two algebraic expressions to compare. Start with the cubes. A cubed is d minus 4 cubed over 216. B cubed is d cubed over 8. And c cubed is d minus 1 cubed over 27. We will now put all three over the common denominator of 216 and expand each cube. Collecting like terms gives 36d cubed minus 36d squared plus 72d minus 72. Every coefficient is divisible by 36, and 216 divided by 36 is 6. So we are left with this cubic all divided by 6. Now for the other side of the equation. We substitute the three formulas into a times d squared plus b times d plus c. We now put every term over 6. We're left with d cubed minus 4d squared plus 3d squared plus 2d minus 2. The d squareds cancel to give a minus d squared. And there it is. We're left off with the very same cubic all divided by 6. Therefore, we have an equality. Hence, the sum of the cubes really is the concatenation. Now for the second pattern. We have different digits and a different trick, but we get to the same conclusion in the end, that the pattern will always hold. Consider the sequence 16, 1156, 111,556. Each term adds one more 1 onto the front and one more 5 into the middle. The claim is that every single one of them is a perfect square. 16 is 4 squared, 1156 is 34 squared, and the last one is 334 squared. Let's prove it in general. Here's the key observation. A block of k1s is just a sum of powers of 10, 1 for each digit. That's a geometric series, and it sums to 10 to the power of k minus 1, all divided by 9. As a quick sanity check, 1000 minus 1 divided by 9 is 111. Take 1156. The 1s take up the first half of the number, the 5 is in the middle, and a 6 sits in the units place. In general, the block of k1s is shifted up by 10 to the power of k, The block of 5s is 5 times the block of 1s shifted up by 10, and then we have the 6. Now we replace each block of 1s by the geometric series formula that we derived earlier. We put everything over a common denominator of 9 and expand. To simplify this expression, we use the fact that 50 times 10 to the power of k minus 1 is just 5 times 10 to the k, and minus 50 plus 54 is equal to 4. Therefore, the numerator is 10 to the 2k plus 4 times 10 to the k plus 4. But we know that x plus 2, all quantity squared, is x squared plus 4x plus 4. So, the whole thing is 10 to the power of k plus 2 all over 3 all squared. One thing left. That has to be a whole number. However, every power of 10 is one more than a multiple of 3. So 10 to the k plus 2 is divisible by 3. For example, for k equals to 2, this gives 34, and 34 squared is 1156. The sequence that we have considered is nothing but perfect squares. We just saw two number sequence patterns, and both of them had clever arguments that turned out to utilize algebra with powers of 10. In both cases, what looked like a coincidence turned out to be a true result all along. If you like these videos, please make sure to like and subscribe for more.